Okay, geometry, we're moving on into section 7.4 now, where we're moving away from parallelograms and now into rectangles. So rectangles are one of those funny things here that obviously you could go to a kindergarten or a first grade classroom and kids there would be able to draw you a rectangle and could tell you what it looks like, but we dive a little bit deeper into that. And we're trying to get a little bit more information about that here. So our definition of rectangle is relatively simple here. So a rectangle is a parallelogram with 4 right angles. But in geometry, you've really got to pay attention to the words right here. Right away, we're saying that a rectangle is a parallelogram. And that's important right there because the parallelograms that we know and love from earlier in this chapter here, let's take a look there, generally would look something like this. And a little kid would tell you these are not the same thing right here. But what I'm hoping we can realize at this level is that everything we learned about a parallelogram right here also applies to a rectangle. What makes it a parallelogram is the fact that your opposite sides in a parallelogram are parallel to each other. And that exact same thing happens within a rectangle as well. The key here now, though, is that all 4 of our angles within this rectangle have to be right angles, all 90 degrees there. Okay, so the fact that a rectangle is a parallelogram tells us quite a bit. So focusing on that word right there, I wanted to talk about this spot right over here. The fact that a rectangle is a parallelogram helps us know a bunch of other things about rectangles as well. So the 5 things we are going to list right here, guys, at the bottom here, are true for all parallelograms. Like, for example, opposite sides in every parallelogram, because of the definition right there, have to be parallel. That's true for all parallelograms, but it's also true for rectangles. And why is that? Because of what we said right here, that a rectangle is a parallelogram. So because this statement right here, number 1, applies to all parallelograms, it applies to rectangles as well. Okay, what else do we know? In a parallelogram, opposite sides, in addition to being parallel, also need to be congruent to each other. And that seems to be happening then within our rectangle as well. So I guess if I wanted to start marking this thing up, the top side and the bottom side would have to be parallel. The left side and the right side would have to be parallel as well, but they also would need to be congruent. Top congruent to bottom, and left congruent to right. So there's a lot of tick marks going on right there. How about number 3 here, guys? Opposite angles in every parallelogram would have to be congruent to each other. Well, since a rectangle is a parallelogram, that same property applies right here. Opposite angles in a rectangle would have to be congruent as well. Now that one's probably pretty obvious because all 4 angles within your rectangle are 90 degrees. So pretty clearly, a pair of opposite angles like this one and this one here would have to be congruent to each other since they're all the same. Now, that actually adds up to something interesting for number 4 then. Consecutive angles in a parallelogram are going to have to be supplementary. Like if we were talking about this angle right here, which looks acute, and this angle right here, which looks obtuse, they can't be congruent, but they do have to add up to 180 degrees. The same thing happens within a rectangle. So consecutive angles in a rectangle are going to have to be supplementary as well. And again, that one's relatively easy to see. 90 plus 90 pretty clearly is going to add up to 180, and that works no matter which 2 consecutive angles you choose. And the last one can get a little bit muddy to put in the diagram right here. What do the diagonals of every parallelogram do? All right, if I tried to draw one in here like this and one in here like this, the diagonals of every parallelogram bisect each other. Or another way we put that in 7.2 is they share a common midpoint. Now, what I would normally do here, let's see, I've already used 1 tick mark and 2 tick marks, so I'd put a triple tick mark right here and another triple tick mark right there, indicating that those 2 halves of one big diagonal are congruent to each other. Now in a parallelogram, don't put this in your notes yet, guys, I would have had to put a different number of tick marks here, like 4 and 4, but I wonder if you guys might think about that for just a second right here and notice something cool about rectangles that didn't happen in normal parallelograms. This piece right here and this piece right here sure look like they're the exact same length. What I'm really saying, guys, is that this triangle right there sure looks isosceles, doesn't it? Like those two sides would be the same. And in fact, they are. So what I'm going to do to indicate that, this you should put in your notes, is I'm going to put a triple tick mark here and here as well. All four of those little half diagonals in a rectangle are congruent to each other. Now that's not the case in a normal parallelogram if I were to draw my diagonals here looking like that, okay? But it does work out in a rectangle. So we'll talk more about that in just a second. So we have our definition. A rectangle is a parallelogram with four right angles, but in addition to that definition there, because a rectangle is a parallelogram, we also know these 5 properties apply to every rectangle as well. But as we were talking about here in number 5, something cool happens with diagonals that doesn't happen in a regular parallelogram. So here's theorem 713. It's the only theorem we have to write down in this section, you guys. If a parallelogram is a rectangle, then its diagonals have to be congruent to each other. Now that has to do with the fact, and I know this year we're not spending a whole lot of time proving theorems here, but that has to do with the fact that if I were to draw a diagonal here that looks like this, we form a triangle that I'm going to kind of highlight right here in yellow. And then if I were to draw the other diagonal in like this, that forms a triangle as well. That would be, let's see, this guy right over here in blue. And with a little bit of work, we could prove that the yellow triangle and the blue triangle are congruent to each other, and that means that their long sides, the hypotenuses of both of those right triangles, would have to be congruent to each other as well. For now, we're going to kind of trust that one to the eye test right there and say, yeah, it looks like those diagonals are congruent to each other. Now, guys, that's it as far as new content right here in section 7.4. So let's solve a couple of problems here and see what we have. So my directions right here for you tell you that quadrilateral WXYZ is a rectangle, and we're going to find, let's see, 1, 2, 3, 4, 5, 6, 7, 8 missing measurements right here to finish this up right here. Okay, first thing, we want the measure of line segment YZ. How long is it? Well, YZ is the bottom side in this figure, and one of the things we learned here is that because a rectangle is a parallelogram, opposite sides have to be congruent in every rectangle. And how long is our top side? 15. That means that our bottom side has to be 15 as well. So the measure of YZ is 15. How about WZ? I want to know how long the left side is now. And again, opposite sides are congruent. So if my right side, XY, is 8, then my left side, WZ, has to be 8 as well. All right, how about the measure of line segment VY? We're looking at this piece right over here now, guys, VY, and that is half of a diagonal. Well, going back again, because a rectangle is a parallelogram, let's look at number 5 now. We know that the diagonals bisect each other. So if this piece right here is 9, this piece in the bottom right, VY, has to have a length of 9 as well. Okay, and now XZ. XZ obviously is this line segment that comes from X all the way down to Z. And to do that, we're going to have to pay attention to this theorem we just wrote down. In a rectangle, your two diagonals are congruent to each other. So we know that the diagonal that goes from W all the way to Y here in red is made up of two pieces that are 9 and 9. So the total measurement of diagonal WY is going to be 9 plus 9. In fact, let's write that out, which is going to be 18. And one more time, the diagonals in a rectangle have to be congruent. So line segment XZ is going to have the same measure there of 18. Okay, that is it for side lengths. Now we start talking about angle measures a little bit more right here. So I tell you what, I'm going to switch colors right here, make that a little bit easier to see, and let's start talking about angles. So the measure of angle, WYZ. So follow it with your pencil, W, Y, and Z. So we're talking about this angle right here, guys. And how big is that? Okay, so the key to this problem is what we said earlier. The fact that the diagonals are congruent means that all four of these little pieces here have a length of 9. And now, if I were to focus on this triangle right here on the bottom, triangle ZYV, with the 9 and the 9, we know that that triangle is isosceles because it has two congruent sides. And that means that it's going to have two congruent base angles as well. So, boy, I made a mess of that. I'm going to undo my shading right there. This angle would have to be 25 degrees as well. One of the things I want you guys to focus on is that unlike a parallelogram, rectangles have perfect symmetry right here. You could just fold this rectangle right over that dotted line and the left side and the right side would match up perfectly. So that's one way you can think about getting from this 25-degree angle to that 25-degree angle. Okay, how about angle ZVY? ZVY is going to be this angle right up here, and we're looking for the measure of that one. Now again, I want to focus on triangles. And one of my favorite things about geometry, everybody, it's true for all of math, but I like it especially here, is that when you learn something new, it doesn't replace something old that you learned, it adds to that. We have learned for a large part of this year certain things about triangles that still apply here now that we're talking about rectangles. And one of the important things we learned back in the first semester is that in any triangle, the sum of your three angles always has to be 180 degrees. And that if you know two angles within your triangle, like this 25 and 25, you can find the third relatively easily. What I would do is go to my calculator and type in 180 minus the first angle I know, 25, minus the second angle that I know. I know a lot of you guys like to add those angles together first and then subtract from 180, and that works too. Either way you do it, the 25 and 25 makes 50, and 180 minus 50 is going to get you 130 degrees for the measure of angle ZVY right there. 130 degrees. Okay, moving on now to our seventh question here, the measure of angle WZX. All right, so W to Z, so I'm going here to here to here. So now we're talking about this angle, and I better do a triple tick mark right there. Okay, to focus on that, let's go back to our very definition of a rectangle, a parallelogram with four right angles. We know that each one of the corners of your rectangle is 90 degrees. So that means that angle Z in total here has to be 90, and we've got a 25-degree angle right here. These two angles here are going to be complementary angles, two that add up to 90. So I would take 90 now minus the 25 that I already have, and we'd end up with 65 degrees now for the measure of this angle. And there we go for the measure of angle WZX. Okay, of course, that same thing is going to happen right here as well because we have another isosceles triangle from W to Z to V. Okay, and the last question, there's two different ways to get, but we should get the same answer if math is actually right. So the measure of angle WVZ. Okay, so where are we talking here? W to V to Z. Now we're looking at, oh boy, I think I need 4 tick marks on this angle right here. Well, two ways of going about it. Again, we've got a triangle right here, and we know two of the angles already. 65 plus 65 is going to get you a total of 130. And if we took 180 minus the 65 and minus the 65, that's going to get you 50 degrees for the measure of this angle right here. So 50 degrees. But the other thing you might have noticed, ooh, this is kind of messy right here, guys. Those two angles right there, oh, they have to form a linear pair. That makes them supplementary. 50 and 130 add up to 180 degrees, which of course they should because you have a straight line right there. So you could have just taken the 180 minus this 130 right there, and that would have gotten you 50 degrees either way. Okay, so two different ways of coming up with that answer right there, and that, you guys, is about everything I could have asked you to find within that problem right there. Okay, so we just dive into the diagram, we just attack it. In fact, when I do a problem like this, I usually just start marking up everything I can in the diagram first and then come back and answer the questions that they were looking for. But anyway, okay, two more for you right here. Ooh, that got a little bit ugly there. Sorry about that. Let me see if I can move things around just a little bit. That can go there. And I think if I do this, that looks a little better right there. Okay, let's run with that. We're going to solve for x. If the measure of AC, which is this diagonal right here, gotcha, AC is 4x plus 11, and then BD, I'll do that one in purple here, from B to D is equal to 10x minus 4. Well, I want you guys to notice right here and to get used to the vocab that AC is a diagonal in this rectangle and BD is the other diagonal. And what do we know about diagonals in a rectangle? Let's go right back to Theorem 713. If a parallelogram is a rectangle, then its diagonals are congruent. Now, I should have put in the diagram here, in the text, that this was a rectangle. My mistake there, guys. But that's what we're going to run with right here. The diagonals must be congruent. So 4x plus 11 has to be equal to 10x minus 4. Diagonals are congruent in every rectangle. Okay, so what are we going to do, guys? I'm going to bring this 4x over to the right. 10x minus 4x is going to leave us with a 6x. And then I'll add that 4 on the left and get 15 right there. Okay, and I was kind of mean to you guys, but I thought, you know what? I should probably start giving them more problems like this. The 6's cancel, of course, and we end up with x equals. But 15 doesn't divide evenly by 6. When you type that into your calculator, you're going to end up with a decimal, which I know really scares some people, but it's not a bad decimal. X is equal to 2.5. Now, the directions here were just solve for x. So it looks like I probably have this one done, but why don't we try just checking to make sure that we got that one right. So where is, I tell you what, I'm just going to go with this calculator right here. And let's see what we got here, guys. I'm going to make that a little bit easier to see. So one more time, we just did 15 divided by 6 and got 2.5. And now I want to use that 2.5 to make sure that these two segments here have the same length. So the first expression we have is 4x plus 11. So I'm going to type in 4 times a 2.5, okay, and then plus 11 at the end of that, and I get 21 now for the measure of diagonal AC. And if we've done this right, we should get the same thing when we put 2.5 in for BD. This is 10x minus 4, so 10 times 2.5, wait a minute, that didn't come out right. I missed my 0 there. 10 times 2.5, but then a minus 4 at the end of all that. Yeah, there you go. Gets me 21 as well. So I've given you guys mostly whole values right here for x most of the year, but we're going to try to do a little bit more with decimals right here later on in the year. So if the decimal scares you, I would understand why, but the proof is right here, guys, that we got this right. It's okay for your variable to be a decimal value. We just need to make sure these two numbers come out to be exactly the same. Last problem I have for you guys is another ugly one with spacing right here. There we go. Okay, solve for x. If AE has a length of 3x plus 2. So let me go to the diagram right here. AE goes from here to here. So you'll notice, guys, that's not a whole diagonal. That's just half of a diagonal. So 3x plus 2, I'm going to write right there for AE. And then BD is given to you as well. And BD goes from B to D. It's this whole piece here in red. And so you'll notice then BD is a whole diagonal, 9x minus 8. So the really tempting thing for everybody to do right here is to just do what we did on the last problem and take the one measurement you've been given, AE, and set it equal to the other measurement you've been given, which is 9x minus 8. But I really want you guys to think hard about what it is that you're saying then. If this is your equation, you're telling me that this piece right here in blue and this piece right here in red have the exact same length. And I think as soon as you look at that diagram, you're going to realize, wait a minute, that's not right. So what do we need to do with this? We need to take advantage of the fact that the diagonals in any parallelogram bisect each other. And that means that from E to C is going to have the exact same length as from A to E. That's a 3x plus 2. And that means that it's two 3x plus 2's that make up this entire diagram. So I'm going to multiply my 3x plus 2 times 2. Another thing you could have done is written 3x plus 2 plus another 3x plus 2 is equal to 9x minus 8. So both of those two equations I have there really say the exact same thing. Either way, let me get rid of that. I'm going to distribute this 2 right here. Either way, you're going to end up with a 6x plus 4 is equal to a 9x minus 8. Okay, I'm going to subtract the 6x from both sides, and that'll give me a 3x on the right. Adding an 8 on both sides puts a 12 on the left, and then we'll divide both sides by 3 and get x equals 4. And before I box that up, let's plug that back in and see where it gets us. Let me go green with this one here. Okay, if x is 4, 3 times 4 is 12. 12 plus 2 makes 14 for the measure of line segment AE. Then, of course, EC would have to be the exact same thing. That would be 14 as well. And how about BD right here, guys? 9x minus 8. 9 times 4 is 36, and 36 minus 8 is going to make 28. Now, does that make sense here? I think it does. If BD, this whole diagonal right here, is 28, 28 is also the sum of 14 and 14. So I feel pretty good about that answer right there, that x is equal to 4. All right, guys, that is everything I have for you here from section 7.4 on rectangles. So let's dive into that homework and see how you do. Good luck, everybody.